Hi, everyone. I'm not going to walk in front of my teammates. Welcome. Good morning. Hope you're enjoying. Hope you enjoyed yesterday. We have a presentation today. The most
it's very tiny on the top.
important slide of this presentation is the first slide, right? Because what we're doing here is, everything good?
Yeah, you're good.
Okay.
Are you switched on yet?
So I'm going to go to this side. What we're doing here is we have Google, GPC, we have Microsoft, Azure, we have Facebook, Meta, and we're here to present our alignment on how we want systems to be built from a security perspective, how we want servers in particular to behave and what interfaces we want to see going on there. And we have the alignment as well with our friends at the two major x86 makers, Intel and AMD. So really this is sort of what we see, the premise and the problem statement. You know, there's a lot going on. What should we actually do? And how do we help burn down and deal with this uncertainty, right? So the problem statement here, what we're trying to address in particular, because security, of course, is a very broad space, is boot integrity and attestation. My system is booting what it's supposed to be booting, and there is a clear cryptographically strong statement about that, right? So typically system integrators come to us, they say, I don't know how to do this. I don't know, there's too many requirements, and all of you are asking for different things. And we on hyperscalers, on the flip side, are saying, you're all building different things that don't really make sense together. And of course, there are too many OCP specs. So really the goal today is to present what we think is, the term is admissible architecture, right? But what we think of it is a framework that we want to be inclusive and extensible and to keep working on for the next several months and quarters. To drive alignment and consistency. So we're going to present one way we want to see systems behave and be built that we feel is going to help clarify a lot of doubt and help people make a system that works for all of us, for Google, for Azure, for Meta. The approach that we're going to present today, so we have a lot of speakers, right? So we have a lot of ground to cover. We're not going to answer all of your possible questions, but we're going to try to answer some of the key ones, right? We're going to start with the capabilities. We're going to establish the devices that we care about, that we want to cover today. That doesn't mean that some devices are forbidden or out of scope forever. But what it means is that we're focusing on the most important things first and what the properties of those devices should be. Then we will talk about interoperability. Once you have individual devices, how do you make it all work together? How do you make it all talk? How do you make it all talk the same language? And that's one of the keys of what we're doing here. And lastly, orchestration. How does a platform come together? When it comes to device selection, we're really going to focus on CPUs, obviously. But more broadly, we're taking a page from NIST, A100-193. What is a server-critical device? Is something necessary and fundamental to a platform. Our focus here as our first set of devices that we care about is on confidentiality, right? If you're handling user data, that's a device that we really need to address immediately. So CPUs, and then what's the next level of things? Smart NICs, GPUs, accelerators. There's a whole other host of devices. We'll get to them. But right now, we need to focus on the more important ones from the point of view of user privacy and user trust. So the first, outside of the framework and what we're trying to achieve, the first important message that we want to convey is this one, right? We're going to be taking a page from NIST 800-193, Platform Firmware Resiliency Guidelines. It says you should build for three things. You should build for detection, which is, I heard Brian talking about this about an hour ago when he was talking about measurable, right? You should know what you loaded. You should know exactly. You should be able to detect exactly what code you're running. That's the point of detection. We're talking about protection, which is critical for people who run very large data centers. You need to be able to reject random firmware updates that are going to damage and cause denial of service at scale. So that's what protection is about, to protect the integrity of a system. And recovery, because bugs happen, because we roll out software all the time, because hard to debug, strange interactions do pop up. We need to be able to bring a system back to a known good state from a catastrophic scenario, and to do this scalably without having to call human ops, because we have lots of machines. So we divide that space and we align it on two axes. Detection is critical to integrity TCV. You're actually, this is what's telling you to trust the code that is running on the platform. So for that, we will lean quite a bit on integrated silicon RODs. Blocks inside SoCs and ASICs that behave as root of trust for measurement. That's their job, measurement. That's how we're kind of putting that guardrail and trying to make it do one thing very well defined, very simple thing, hard to do it right. So let's focus on that for that part of the world. When it comes to availability and dealing with firmware pushes at scale, rollbacks, situations, all that kind, we're instead leaning on a discrete ROT, which is an external chip, which is something that can be as well a relatively simple chip that has a very important job. So that division allows us to modularize, compartmentalize, and limit the complexity of what goes inside an SoC and derive a common implementation for the layer that goes outside. The other critical property is that when you're building a discrete ROT, you can put flash into it, which is not as easy to do when you're working inside an ASIC. And that flash gives you, essentially, for practical purposes, unlimited renewability and control over versions and control over transfers of ownership and controls over rotations and whatnot. So for the rest of the presentation, we will be having the rest of our partners here, and now it's Indy from Meta's. Your turn.
Thanks so much, Andres. Hey again, folks. I'm Indy. I work as a security partner for Meta. So over the next few slides, our goal is to establish a common understanding about the core functionalities of a root of trust. Let's start with the root of trust for measurement. And let's talk about what a possible implementation of a RTM could look like and some of its properties. So first off, an RTM would most likely consist of its own dedicated microprocessor, along with a cryptographic engine with side channel resistant implementations of common cryptographic algorithms. We would expect it to have some form of one-time programmable memory, which we can then use to provision identity and cryptographic secrets. Most importantly, the RTM must be the first element to come out of reset when the board is powered on. The RTM should be able to measure all the firmware, no exceptions, all the firmware that is running on the device, and control the reset of other subsystems of the device as well. And finally, the RTM should have an implementation of a reporting agent. And essentially, we should be able to query the reporting agent and ask it for an unforgeable attestation token, which allows us to trust the firmware running on the device. Moving on, digging a little bit deeper into establishing the identity of the RTM, we believe that it's important to establish identity by composing together various components of the identity distributed across the supply chain of the device. So typically, the way we would compose and construct a unique immutable identity would take into account the manufacturer as well as the hardware identities, which uniquely identify a part in the supply chain. These must be immutable for the lifetime of the part. These would then be used to establish an owner identity during the ownership transfer process. And finally, at runtime, we would take into account, we would bind these together along with the bootloader and the firmware identity of the device to establish a trustworthy, unique, and immutable identity in our infrastructures. The measurement flow obviously follows a very similar route. We would expect the device to boot up from a ROM, an immutable code in ROM, which then verifies the integrity of the various stages of the bootloader, which in turn goes on to verify the identity of the firmware. So let's quickly also talk about the root of trust for update. The RTU is responsible for ensuring that only a legitimate update can be flashed on the device. Why do we need this? It's because for large, hyperscaled environments with automated fleets, the update path can actually serve as a denial of service if a threat actor is able to use this automated update path to flash corrupted firmware on hundreds of thousands of hosts at the same time. They will have achieved their end goals of denial of service. So the RTU has three basic requirements. First, complete mediation. The RTU must be able to mediate the untrusted out-of-band or even in-band path, which is used to flash a firmware update package on the device. There should not be any sideband interface or any interface to bypass the RTU. Secondly, it should reject unauthorized read and write requests to the spy flash at runtime. And thirdly, it should essentially enforce the resiliency policy, which consists of, hey, what should the firmware signature look like? What public keys do we trust? What is the rollback policy? And what is the key revocation policy? And finally, coming to the root of trust for recovery, once again, for hyperscale environments, the manual intervention-based operator repairs, they simply do not scale. So what we need here is an automated, reliable, and secure path for a local recovery in the case that secure boot or measured boot indicates that the firmware has been corrupted. There could be many ways of accomplishing this. One example, simply an example here, is to implement two sectors or even two discrete flash devices. Let's call them A and B. A, which is the primary flash, the machine always boots up and executes out of the primary flash. And firmware updates are always written to flash B. And you can only reboot and update the device if the firmware update has been authenticated. So for the rest of it, let me hand off to Alberto. Thank you.
Thank you. Is this okay? Working. Good. Okay, so Indy described the functionality of the roots of trust, how you implement them, not how you implement them, but why they're important, what kind of protections they provide, and gave some hints as to what functionality is really critical for them. Now, I'm going to talk a little bit about how we interact with this roots of trust specifically, right? You need code outside that is able to interact with them, to get information, and so on and so forth. So for the RT U1 RT recovery, we're expecting, or we're proposing that the interactions are going to be through PLDM. And for the RTM, which is the root of trust that guarantees things like this secure boot, and that's a lot of other important information specific to the environment that you're running, we are proposing SPDM, meaning any root of trust that is available out there that is doing RTM type of work should be able to respond to SPDM commands, and the way to communicate with it is through SPDM. Now, these roots of trust, we are expecting that they're going to be used primarily in out-of-band type of settings in the servers, like from a BMC or out-of-band type of connections, physical connections. And as such, they're going to rest on top of MCTP, which in turn will rest on top of a physical bus, which we're proposing to be I3C. Let's see. Now I'll talk a little bit about SPDM. SPDM is an interesting protocol in that most of the functionality in SPDM is optional, with the exception of these two responses and two requests at the top. So you have to define a profile to say, if you have a device that is to participate in this architecture, what kind of functionality should it be supporting from SPDM? What kind of commands do we expect that it is going to respond to? And specifically, this profile that we have now concentrates on identity, which is how do you know that that device came from a specific manufacturer, and that is and that is authentic. Then authentication, which is how do you verify that authenticity? How can you do a challenge to that device? And through cryptographic means, have that device tell you that it actually is what you expect it to be. And then finally, and this is a very important one, is the attestation part, which is I want to have the ability to go to a device or a platform in other cases and say, I want you to tell me exactly what firmware you booted or what commands, what configuration you have in place, and any other information that is relevant for me to ascertain your trust level. So this is the profile that we are proposing. And one thing that I'd like to mention is that all of these things, we are pointing in a direction, and a lot of this work and discussions are happening in the OCP security work group. And we are definitely, like we've been saying, we're very open to comments and suggestions and participation of people and things like this, like the profile, for example. If somebody believes, hey, there's some other command that should be included and so on, we're definitely willing to listen. Now, I'm gonna take this RTM in particular and put it in the context of a solution. In this particular case is, how do you do protection for the supply chain, right? Ultimately, what you wanna do in the supply chain is you want to create a device, send it over the supply chain, it doesn't matter how many different paths there are, and when it finally reaches its target, you want the owner or whoever is getting that device to be able to verify that that device is exactly what the manufacturer sent. So how does that work with the context or with the support of root of trust of our RTM is the manufacturer is specifically going to provision certain information in the device, like configurations, policies, and of course the binaries that are running, and also certificates that basically allow people to verify the identity of that device. And then at the same time, the manufacturer also needs to create a reference. This is document that says, this is what this device looked like when I sent it out. And ultimately what you want is down here, this verifier is supposed to interrogate the device. This is using SPDM, for example. Take the references and compare the references and what the device is saying, and then make a decision as to whether or not that device is what the manufacturer says it is, or is configured like the manufacturer configured it. Now, one thing that I'd like to clarify here is that this specific example is for supply chain, but this type of thing happens all the time in data centers, which is if you do updates of a device, if you change firmware, for example, or if you change devices in the platform or those kinds of things, you need to update the references and you need to check that those platforms are what you expect them to be. So even though the example here is very specific to supply chain, it also applies to what happens when you're in a data center. Now, how do you do that stuff that we did before, right? Which is, how do you make sure that those references that the manufacturer is creating and the information that the device is reporting throughout the station, how do you know that, how do you make sure that those things have a coherent format so that ultimately you can have a verifier at the bottom that is device independent, right? You don't want to have a verifier for NICs and a verifier for SSDs and a verifier for all kinds of devices. You want to have some schema that defines how this information is put together. And for that, we are proposing CoREM, which is a standard that is in development at TCG. The TCG DICE working group is specifically working on this, is going to ballot maybe this month or the next month. And the idea with this is that you would have a schema that describes exactly how to put this information together. And at the same time, the expectation is that SPDM is going to provide an option for have measurements that align to that schema. So ultimately, when you're working as the verifier, what you have to do is you can look at the reference, you can look at the value, you can look at labels in both cases, compare the labels, and if the labels are the same, then you can compare the values and make decisions as to as to the trustworthiness of that device. So now to tell you a little more about the architecture and how it comes together is Brian.
Thanks, Bert. Okay, so bringing it back together, we heard Andreas talk about the root of trust for measurement, the root of trust for update, and a root of trust for recovery. So this is how it comes together in a system architecture, where we have the root of trust for measurement in the components, all report back to the platform root of trust, the protocol being SPDM, and the protocol for measurement being SPDM, the protocol for update, as you see on the side, being PLDM, and the platform root of trust being the component there for aggregating all of these together. So we talk about the NIST 800-193 platform firmware resilience guidelines, and it mentions the detection, protection, and recovery. We talked about the root of trusts for each of those roles. The detection, we would aggregate the measurements from the root of trust for measurement, the RTM. That would get aggregated via the control plane, taken out of the server to a trusted verifier, or an oracle that's going to determine whether the system gets a attestation token. With the protection for out-of-band update, and then we have recovery, the root of trust for recovery, for out-of-band recovery that bootstraps that platform, and we see recovery coming through the VMC. And this is how it looks as we put it all together, going back to that original diagram in a composable admissible architecture. We have the components reporting back SPDM to that VMC, and the PLDM for the root of trust for update, the protocol communicating out to all of these devices for their updates, and then of course those measurements getting taken out to the trusted verifier to make a determination as to whether that system as a composite is trustworthy. So now I'll hand over to my good friend Prabhu.
Thank you, Brian. Good morning, all. As you can see, these specs are not unfamiliar specifications. They're already in our hands. Quite of them are being developed within our work group, OCP work group. The key thing to reflect for myself and for the team is about 2+ years ago when we all met together and said, what do we do from peripheral security standpoint? We kind of called out, we need to draft out what is the architecture that we want to pursue for each of the peripherals. And in that conversation, we kind of called out, there are devices that are really good at doing security. Some of them are really mature. There are some that kind of sort of do it. There are devices that kind of tuck behind some device that is a bit more smarter, a bit more secure, take the chain of trust services. We started working on proposals to drive that architecture, and here is a step towards what we call as the critical devices that touch the user data, and how we build admissible architecture for these devices so that we can orchestrate them through a known entity with clear roles and responsibilities. Okay. As we has been drafting the platform root of trust specification that talks about the orchestration part. And now in this storytelling, what we are trying to get is the RTU and the RT rec, the recovery aspect of it. It's better stay with an orchestration device, and all the devices that are critical devices, they raise their bar in aligning to a minimal set of capabilities that we call out as part of our specifications and be orchestrable in a meaningful way by attaining interoperable capabilities. As Bert talked about SPDM, we have a call out here to say SPDM allows us to provide measurement blocks. Now it's establishing some specificity on what those manifests are going to look like. How are those values are going to come across the wire for the orchestrating device to attest the device. And there are quite a few documents that are being talked about. Earlier, Brian, Elaine, and Yigal talked about some of the checklist aspects. Attestation spec, which was one of the first ones we started drawing out. So the key takeaway for me is to increase the agility of the documents that are coming out of our group and start intercepting products that are on our roadmaps as quickly as possible. That will lead us towards securing our platforms much more faster. Let's set what that minimum bar is going to look like. Okay. Thank you. I think we can open up for questions.
Thank you, Prabhu. Right.
Thank you.
Well, thank you. We're open for questions. We're ahead of time. That's something very interesting. I think our message is relatively complex and rich, but we were able to provide it in a sort of concise way. So we're looking forward to your questions.
So the part of this where you're creating a standard interface and identity seems well-defined. Do you have any, how strong of a statement do you want to be making on out-of-band recovery? Some examples I could think is, one, you could say, you should rely on a BMC to be able to update BIOSes. Or you could make a stronger statement of the external root of trust managing that flash should be able to force an update. Like, how strong of a statement do you think you're going to have as part of this activity?
Do you want to take it or do you want me to?
Yeah, I can, or if you want to take it.
Go for it.
Yeah, so in some cases that BMC, as you mentioned, is that root of trust on platforms. We'll look at BMCs in the industry today. The security that they have is not quite where we'd like to see it. Going forward, I think that gets a lot better. But I think you'll notice that first, the part of your question is about out-of-band and out-of-band recovery. I think out-of-band is really critical. You don't want to rely on the update mechanisms or recovery mechanisms being in-band, especially as a hyperscaler. You have different architectures, and you may not always run your software on those host processors. The control plane, I think, or management plane, which we call it BMC, is just about that out-of-band recovery. The mechanism for recovering the BMC itself, because it can be quite brittle without the right security there, is typically a platform root of trust component. Now, is that necessary going forward? I think once we get the right security capabilities, maybe in BMCs, we could see that evolve and change. But the architecture today is there's a component for securing the BMC.
Okay, thank you.
So boosting Brian's signal. So two key abstractions. The first one, at Google, we like to say a lot. We have this mantra that we put 2 layers of security around everything, right? So recovery is about denial of service, which is a security risk. So we're talking about 2 layers here, the AV recovery and the BMC out of band. And the other one is there needs, it's not turtles all the way down, right? At some point, something has to autonomously recover the BMC. So we're trying to keep that recovery foothold to as minimum as possible. Eventually nil, that's a nice thing to shoot for. We'll be happy when we get there. Next.
A pretty simple question. So you talk about I3C. Are you trying to push I3C as a mandatory things inside PCI Express or other interconnect standard?
I3C, the current proposal is to use the I2C, the SM bus connectors or pins, so that is perfectly backwards compatible with I2C. And then there is also a device, a hub, that allows you to have both I3C and I2C devices on the same platform. And it avoids all of the issues that we've run into with I2C that are specific to multi-master. And there's a bunch of things like that that are problematic. So the current approach is to make it fully compatible. Basically, if you have a connector that does I2C, it can do I3C.
Yeah, I perceive being nice with existing hour, but like, do you want to push, I don't know, PCI Express Gen 6 to be mandatory to be I3C? Because, you know, like there is a lot of inertia in the ecosystem. So like if there is no push from like a standard body like PCI Express group to say, hey, everybody, you should move to I3C, then you can have like kind of this mismatch that can stay and prevail for a long time. So.
Yes, we are specifically working with PCI Express to officially make I3C part of their standard.
Okay, thank you.
I think we're saying pretty loud and clear, not I2C, right? it just,
Yeah.
you know, its time has passed.
Yep. It's too brittle.
One follow-up for this, and then I have another question. So I3C versus USB, there's been discussion in the past about trying to use USB for that. What's your thoughts on that?
Well, we believe that they're not mutually exclusive,
Okay.
right? You don't have to do or stop doing one to do the other, right? Now, if you want to get into the standardization and all that kind of stuff, is a completely different discussion that I'm not prepared to have here anyway. I don't know if anybody else has opinions, but specifically, we don't think that they're mutually exclusive.
Okay, so you think of it as at least I3C, but if there will be an MCTP over USB, that's also acceptable?
We'll take it.
Yeah? Okay.
Yeah, I mean, that has implications on whatever that central place is that is talking to all the different devices, right? In terms that it needs to support potentially two different physical protocols, right? And maybe needs to have two sets of connections. All of that is potentially an issue when you're building a platform, right? So having these mixed systems is problematic, but architecturally, we don't think there is that they really conflict with each other.
Okay, cool. Another question we discussed yesterday a little bit, but I want to hear your thoughts here. You're making a distinction between what's in silicon, which is the RTM, and external, which is the RTU and multi-rack. Can you talk about why you believe the external one has to be external and not in silicon? Or in package in some way?
I can take that.
Yeah. So, you want to take it? Or you want to?
Go.
So, I think, recovery, like if you just look at recovery and devices self-recovering, they're generally, you'll come to the conclusion that there has to be an external entity that's orchestrating that. Like devices can have some dimension, some element of recovery, like Indy talked about the AB flash mechanism. Well, what do you do when both of those are corrupt? You get maybe bit rot in one, or there's some implementation issue, signing gets compromised, both of them get compromised. How do you recover that device from like an immutable source? Does it have that self-recovery? It's pretty complex to start to design into devices a self-recovery mechanism for bare metal. You'll see with the recovery specifications we have in the works, as you know, in the open compute. It's looking at an external entity that can provide that fresh payload. Well, so that's for recovery, and I think you'll agree with that one, that there has to be an external entity to drive it. And then when we look at update, the root of trust for update, you get to a similar thing in devices determining reasoning about whether they should or should not take a particular payload, that it's a lot easier to design that centrally and to orchestrate that from a central entity.
Okay.
So that's how we come to the determination of what really goes where in a system architecture. It's just running it to ground and seeing where these components best fit.
Yeah, it's a little bit different than the approach we had initially, which says we want to set the requirements and not require a specific discrete chip on every device. So that's why I'm trying to understand the rationale.
Yeah, so we set out the requirements, but then the question that came back was, how does it all come together? I love the first slide or it's like the first or second one with this one. How does it all come together? Like what do we build? And this presentation is about clarifying how it all comes together and what to build, and hopefully that's the clarity we provided.
Okay.
Yeah, but by the way, something to point out about this architecture is that the proposed implementation of having this thing centralized makes a lot of sense to a lot of data centers, right? But the architecture itself allows you to have more complex implementations of this, where you can have multiple RTUs or RTUs that are in devices or in cards or things like that, right? Architecturally, there is nothing that says that you cannot do that, right? The guidance here is, these guys have done it for a living for a long time, and they're saying, for us it's much easier if we keep this thing centralized.
Let me quickly touch on another business requirement here, is that we want to minimize the cost of verifying the RTU and the RTREC. The way we think we can do that is by having a discrete RTU and RTREC, which we can provision, integrate over multiple generations of servers, which we can verify once and simply, to use the term, plug into different iterations or different generations of the server. That would help us amortize the cost of verifying and maintaining the RTU and the RTREC over multiple generations of servers.
Okay, thank you.
If you're having an external and internal root of trust trying to attest for the same piece of firmware, how do you mediate any disagreements between those roots of trust? Is this something that can be, is this by a centralized policy, or is this through the recovery mechanism?
Oh, I've got one. Did you take it?
Whoops.
So, yeah, when you have a discrepancy, or a mismatch between, what's been reported by this platform root of trust and this internal root of trust for measurement. If you look at the earlier in the slide, there was a trusted verifier that sits outside the system, like cloud attestation services. That makes the determination on what is the truth. And when you get a truth mismatch, that's when you go into your recovery flow to bring those into policy. And then I think earlier Bert went through some of the manifests and manifest formats that we're looking at, and then how those reflect, because measurements reported from a root of trust for measurement may be different to a composite measurement that you take of a big firmware binary or blob, which is a composite of lots of different ones. So the root of trust for measurement may give you 4 measurements, whereas your platform root of trust or your system oracle may see this composite binary. Well, I think the manifests explain what each thing should should report and should see, and the verifier, the cloud service, has a view of what that should be. And then if it's a mismatch, you got to go to recovery or update to put it right.
So would it be fair to say that you have these multiple measurement points for explicit attestation, but for any sort of implicit attestation, you like determining if things should come out of reset or things like that, there is kind of a central point of, a central, is there a point where you say, this is the person that decides this piece comes out of reset, or this piece gets any secrets unlocked, or things like that?
I think that the component that does that is the trusted verifier up here. It gives it a token or a sealed secret if everything checks out right.
Okay.
One more very small detail. We're not just measuring code. We're measuring configuration as well. Right? It's important to customers to know that we couldn't, do some JTAG games underneath them, right? And that has to be measured as well.
One more question. So if you have like a discrete RTU, do you take into account a treat model where you have an interposer between the discrete RTU and the ASIC? Somebody on the H3C bus that is trying to intercept the firmware being uploaded to the ASIC?
So this is one of the main reasons why we're doing this split, right? This is why we need the root of trust for measurement in the ASIC, north of any interposition. North is it's a relative concept, but I think it drives the message. Thank you. If you're interposing on my update path physically, that's not a huge risk for me because you're messing with the update path of one machine. Remember, we need to defend against denial of service at scale logically. So that's why we compartmentalize it that way. Whereas if you're delivering, that interposition that you describe is not going to fool my root of trust of measurement into providing to a trusted verifier something that it has not loaded. So that's why we're doing that.
Yeah, so the RTM attestation inside the ASIC is monitoring, and that's a real key here, all right?
That's right.
Okay, thanks.
Yeah, one more thing there is that the amount of protection that you have to provide between the device and the RTU is sort of specific to your implementation, right? You may decide, for example, I'm really concerned about having interposers in my architecture, in which case you have to create a secure channel between the two. Obviously, that requires a more expensive device and a more advanced RTU. Or you can say, no, I'm designing my platforms in such a way that putting a physical interposer there is a low risk. It's something that is easy. And then in that case, you don't have a special channel, right? But you always have to have this. There has to be a secure, based on your requirements, communication between that RTU and the device that is getting the updates.
I think we got
We'll take the last question.
Hi. One of the complications here that I could see is the timing of whenever the trusted verifier will reach out and check the machine. Do you have any thoughts on how to handle, say, after you do that check, the full machine changes attestation state, or maybe just like the GPU had a power off because it's on a separate power domain or something? Like, I was just wondering if you have any thoughts there.
Yeah, I do. I have a lot of them. Yeah, the order of measurement really matters, and like that, one of the things Andreas mentioned was we're not just measuring. It's not just measuring code. So what you're measuring is the device's state, and it can maintain that state post, measurement. So it has the right integrity to maintain policy. So it can maintain the attested state even across a reset. If it's reset, it's coming back to the same state. So you're measuring not just code, but configuration, also security properties, and so on.
Okay. Thank you. I guess I'm also a little curious if there was like a more active intruder or something trying to muck with this, and maybe they were purposefully reflashing the GPU or something and pulling the power and plugging it back in.
So part of the protection that the RTU provides is it prevents runtime, not RTU things from being able to flash the memory of the device, for example. So there's active protection, number one. Now, that said, there is potentially devices that allow runtime updates, and that's a lot more complicated, right? Because if you have already given your secrets to a device, there's not much you can do to take them back, even if you get notified that an update just happened, right? So then there's provisions where you can say something like, I really trust this device. I'm going to give it something that is very, very sensitive, security-wise. So please don't update this thing while I'm using it, right? And then there's flags that will honor that and say, and all of this is part of how you implement this RTU type of functionality.
All right.
Thank you for the question. I mean, we don't have all the answers, right? So
course.
this is whiteboard session time, and that's great. Thank you.
Thank you all.
All right, I think we're good. Thank you, folks. Appreciate it.